Hi everyone, it's Mr. Hamilton here, and this video is on the motor principle. Now you'll notice we have two bar magnets and a current carrying wire carrying a current in conventional current into the page in front of us. And what I want to do is I want to just note the direction of those fields that are going to be formed around the wire and also between the north and south ends of the magnets. So we know that externally to a magnet, the magnetic field lines go in this direction, always from north to south, and inside a magnet they go from south to north. And so obviously we're going to have a bunch of field lines that are going to do this as well, going like this, but we're not going to draw those for the purposes of this diagram. We know we have all those, but I want to focus in and zero in on this area where we have interaction of the magnetic fields. So we have that idea, and then we also have the first right-hand rule, and that is our thumb is in the direction of the current and our fingers wrap in the direction of the magnetic field. And so if we use the right-hand rule, not the left hand, to do that, then we see it wraps in that direction. And as we note from before, fields in the same direction, they repel. So the same direction repel, and fields in the opposite direction, they attract. So we noticed that from our last lesson. Opposite direction, attract. And so the idea here is that this is going to move in this direction. We're going to experience a force that is downwards in this case. So we've got this external magnetic field from the magnets, we've got this induced magnetic field from the current carrying wire. And Michael Faraday was the one to actually take this and now derive what we know as the motor principle. He actually made a motor using this. So Michael Faraday, that was the guy's name, used this principle to make a motor. Not the principle, it wasn't a person at a school, but it was the principle to make a motor. And here's what the motor principle is. It's a very simple principle. It's a little wordy, but it's pretty simple. It simply states, it's stated as this. It says, a current carrying conductor or wire that cuts across an external magnetic field experiences a force perpendicular to both the magnetic field and the direction of the electric current. So I'll write that down here, pause the video, and you can write that down as well. So the motor principle says a current carrying wire, current carrying conductor, that cuts across an external magnetic field, so in the diagram above we have this external magnetic field, experiences a force that's perpendicular, 90 degrees, to both the magnetic field and the direction of the electric current. So you can see here that the force is downwards. That's at a 90-degree angle to the external magnetic field. The external magnetic field is going from the left to the right here. And the direction of the electric current is going into the page. So there are two ways we could be perpendicular. We could be going up or we could be going down. And in this case, it's going down. Which brings us to our third and final right-hand rule. Right-hand rule number 3. This is for the motor principle. So you could say it's the right-hand rule for the motor principle. The first thing we do is we put our fingers, it's an open hand. All right, so it's worth noting this is an open hand. And our fingers are going to go in the direction of the external magnetic field. Fingers point in the direction of an external magnetic field. That's what our fingers are going to do. They're in the direction of the magnetic field. The next thing we're going to do is we're going to put our thumb in the direction of the current. And I guess we can be more specific. We're always doing these right-hand rules for conventional current, but it's in the direction of conventional current. So thumb is in the direction of the current. And then last, you're going to put the palm in the direction of the force on the wire. So the palm pushes in the direction of the force on the wire. So try this with this particular example. Our fingers point in the direction of the external magnetic field. So that's going from north to south. That's going across the page from the left to the right. your thumb is pointing the direction of the conventional current into the page, and the palm, if you've done this properly now, is facing downwards. In other words, your palm would push downwards. So that you know the force is going to go downwards. Make sure you practice it yourself and don't just take my word for it. I'm going to give you 2 questions now in which I want you to try to figure out using the right-hand rule. So you need to pause the video and try this out for yourself, draw the diagrams, and then use your right-hand rule to try this yourself. Assuming you've tried this and you have an idea of which direction they're going to go, let's take this up. So what we have in this case is we always have it going from north to south outside of a magnet. And then our fingers are in the direction going down. Our thumb points out of the page, and the force in the direction of our palm is in this direction. So the force is going to be in that direction. In the second case, after you've tried this, you should do this. We're going again, the external magnetic field is in this direction. So our fingers are pointing from left to right. Our thumb is pointing down, and our palm is facing out. So the force is going to be out of the page in this particular case. So that's using the right-hand rule on the motor principle. So let's now see how that applies to a DC motor. So very simply put, I'm just going to draw a 3-dimensional diagram. So stay with me that it's 3 dimensions for a DC motor. So let's assume that we have an external magnet that's north. There's a south end over here too. I just haven't drawn it in there. And then we have a south magnet here. And then what I'm doing is I have a wire that's going into the page in a 3-dimensional way. So it's going in like this, it's going in, it's going back across, away from us, far away from us, then it's coming back out, and then it's coming back out there. So this is going into the page, and then the current's going to travel in such a way that if we're going from positive to negative, the current's going to go this way, around into the page, go across from the left to the right, then it's going to come back out of the page, and back to us again. And so I haven't drawn the complete circuit, but you could say, well, we could complete the circuit, but the point is to see the direction that the current's going and use the right-hand rule to determine what way this motor is going to spin. Because we have a current on this side, on the left side, right here, that current is going into the page. If we put our thumb in the direction of the current that's going into the page, and our fingers are in the direction of the external magnetic field, which is going left to right, then we can see that on that left side, it's actually forcing it downwards. So over here, based on the right-hand rule, the force is downwards. Likewise, over here, when it's coming out of the page on this side right here, we could say that because, again, we've got our thumb is in the direction of the current, our fingers is in the direction of the external magnetic field, which is left to right, the palm of our hand is going to point and force upwards. So the third right-hand rule is going to force this upwards. And what you're going to get is you're going to get this whole loop of wire to begin to turn in a counterclockwise direction. So let's consider after a half rotation. What's happening when it's spun halfway around? Here's what's happened. Again, I'm going to draw the same diagram. I'm going to have this as my external magnets aren't going to change. This is still a northern pole on that magnet, still a southern pole on that magnet. And then if it's gone halfway around, so I've flipped it 180 degrees, what we now get is it's going to look the same in terms of the wires, how those are concerned, but what's happening now is this has become the positive side and this has become the negative side. And so if we were to draw the currents, go in this direction, so going into the page on the right side, coming out of the page on the left side, and we would use the right-hand rule again to determine which direction that would spin. So if I use my right-hand rule on the right side of this side over here, I'm going to notice that the current's going into the page, so my thumb's pointing into the page. The external magnetic field is in this direction, so my external magnetic field is going left to right, and that's going to force it downwards. Over here, thumb isn't coming out of the page. Again, our fingers are going to the right. It's going to force it upwards. And so what we would see here is we would see an effect where initially it forced the thing in a counterclockwise direction, and now when you get a half rotation around, it wants to force it in a clockwise direction now. So what do? This is going to go in a counterclockwise. It's worth noting that below. and then we have this clockwise direction. Well, what's actually going to happen when we do the clockwise direction? Well, what's going to happen is it's just going to go back and forth and eventually stop. So what we do in order to get it to spin is we introduce this idea of a split ring commutator. A what? A commutator. A commutator is something that it's a piece of metal, and when we attach it, it's going to look something like this in a circular fashion. And then when we bring the current in, we bring it with a little metal brush on each side, and we attach it to some battery over here. Here's our battery. And then we have a loop like that. And so what happens is every half turn, you'll notice right here and right here, there's a little gap. And so every half turn, what happens is these little metal brushes, this one here and this one here, touch the opposite side of that commutator. And what that does is it actually switches the direction of the current. So if we had the current switched here, if instead of the positive being on the right and the negative being on the left, if it was the other way, we would find the force to continue to be counterclockwise instead of clockwise. And so that's the principle behind these. We want to use this split ring commutator to continue to allow it to spin in the same direction that it began spinning in. And that's the genius behind what Michael Faraday thought out to cause the motor principle to work. So there you go. If you have questions about that, as always, feel free to ask. Hope that makes sense, and I'd love some feedback. If that does or doesn't make sense, let me know what you think.